But I'm going to speak about foundations. So we transform ourselves back roughly 130 years in time. So we are at the end of the 19th century. And the mystery then was to explain why, if we have hot material, like an iron bar, we heat it, or we have the sun, we know that it emits light, and the emitted light depends on the temperature. If you heat only a little, it's reddish, and then it becomes yellowish, and eventually becomes whitish and bluish, and so on. So how can we explain this? And at the time, thermodynamics was relatively well understood, but the theorists didn't manage to get a theory that matched the experiments. Okay? So then enter Max Planck, and he did a fun thing, I think. So he just said to himself, I'm just postulating that light doesn't come continuously like a water flow, but it comes in small bunches. Okay, he called them quanta. Today we would call them photons. Okay, and he also postulated that the energy was proportional to the frequency. And just by making this assumption out of nowhere, in a sense, he managed to fit the theory, the thermodynamics, to the experimental facts. The irony is that apparently he didn't quite believe in this himself. Okay, he didn't believe that his quanta actually had a physical correspondence. It was just a neat mathematical trick to make the theory fit the experiments. About 20 years later, someone who took his theory at face value was Albert Einstein. So he used this to explain the photoelectric effect. So what is that? Well, if you shine light on a metal surface, the light will make the surface emit electrons, provided that the frequency of the light is high enough so that the energy of every quanta is high enough. If the energy per quanta is too low, it doesn't matter how much light you shine, no electrons are emitted, okay? And this was an important step forward, so this is what actually earned Einstein the Nobel Prize in 2021. And then from there on, this idea of quantization took off, and together with notable people like Schrödinger, Heisenberg, Bohr, von Neumann, and Dirac, they developed what today is quantum mechanics, quantum theory. However, anyone who has studied quantum mechanics, I think, find it quite, how should I say, abstract to begin with. You have something called a wave function, which contains everything, but what is it, okay? So, although we got the theory, self-consistent theory, it took decades before people could really interpret the theory and say, what is the connection between the theory and the experiments we can do? And to some extent, this is still going on. Quantum mechanics is still quite enigmatic in parts. However, this led to what is called the first quantum revolution. So we got many nice things here. Material science, diode, transistors, nuclear spin resonance. We even influenced legislation. Today, you cannot use incandescent lighting, right? We must use LED lighting to save energy, right? So quantum mechanics actually changed the legislation in Europe, okay? So why do we call this the first quantum revolution? And the reason is essentially that all these phenomena is based on collective quantum effects. So it's not what a single quantum system does. It is what many quantum systems together do. So I told you that quantum mechanics is enigmatic because it gives counterintuitive predictions. For instance, uncertainty. Einstein didn't like uncertainty. He said that God doesn't play dice. Okay? He thought that the world should be deterministic. We get non-commutativity, and Professor Leuchs is going to speak about that soon. We get superpositions, namely that things can be here and there, in some sense, at the same time. Okay? And this is not how we perceive the world. So either I'm here or I'm there, but I'm not here and there at the same time, right? We have something called spin. I will speak a little bit about that. We have the exclusion principle. And finally, we have something strange, which is a consequence of the superpositions, which is called entanglement. And in 1935, these three gentlemen, Einstein and Podolsky and Rosen, they wrote a paper called the EPR paper. The EPR is the initials of each of them, EPR paper. It's a very famous paper. And they were deeply disturbed about this entanglement phenomena. So I'm going to explain the essence of what they were concerned about without using their example. I'm going to use a different example, which is actually simpler. So imagine we are where we are, namely at Bari. And then we send out two particles, a red particle this way and a blue particle that way. And we can send them very far away, okay? And then we have people on each side that receive these particles and store them. And then at some moment, one of them decides that they are going to measure the rotation of these particles, okay? So this is called a spin, okay? And the spin can either be up, and that means that it rotates this way, or it can be spin down, and then it rotates the other way, okay? And so just to make you relax, this is the only equation I will show, okay? But I allowed myself one equation, okay? So what does it say? It says that the person here, if he or she measures the rotation, they will equally probably see that the spin is up, that is, rotate one way, or that it rotates the other way. And there is no way of telling which way it's going to be. This is totally random, but it's going to be one of them. The equation also says that the blue particle will also, I have to be careful here. The blue particle will also either spin down or spin up. But what the equation also says that if this particle spins up, then this one will instantaneously spin down. And vice versa, if this is found to be spin down, this will be spin up. And this happens instantly. There's no time delay between this, and it doesn't matter how far these particles are apart. And this really disturbed these three gentlemen. They thought that this is not reasonable. A cause should have an effect. An effect should not be able to be propagated faster than light. But here it was instant, okay? And this was the basis for the paper. And the conclusion of the paper was that either quantum mechanics doesn't tell the whole story. It must be incomplete. Or, if it is complete, then quantum mechanics is non-local, which they thought this is not plausible. So, and especially Einstein, for the rest of his life, was very unhappy with the fact that this entanglement was a non-local effect, it appeared. Okay, then we fast forward 30 years. And then a guy called John Bell, who was a nuclear physicist, but who liked to do quantum mechanics essentially in his free time. So he had a private interest in quantum mechanics. He proposed an experiment where if the results were in accordance to quantum mechanics, this experiment would rule out any local theory, not only ordinary physics. You could cook up any crazy theory which assumed that you had to have a causal correlation effect, okay? So quantum mechanics violated this, okay? So again, I'm going to give you an example, which is not John Bell's original example. This is a simpler one, but it tells you the story. So first of all, let's define something called a correlation coefficient. So this is the degree of how much things are correlated. And the correlation coefficient, per definition, goes from -1 to 1. If it's -1, you have perfect anti-correlation. So this is what we had in this example. If one spins up, the other one spins down. And if the first one spins down, then okay. So you have perfect anti-correlation. If the correlation coefficient is 0, they are completely independent. There's no relation whatsoever between the two events. And if it's +1, you have perfect correlation. That is, they will spin in the same direction. So here, clearly, we have correlation coefficient -1. But now suppose we don't measure the spin in this direction, we measure the spin in that direction. Okay? And the amazing thing is that for this particular quantum state, you still get perfect anticorrelation. So you get -1. And if you measure in that direction, you still get -1. Okay? So if you sum these correlation coefficients in the three directions, three orthogonal directions, you get -3, right? You can quite easily prove that for any local theory, it's not restricted by physics. You can cook up any local theory. The correlation, sum of the correlation coefficients in the three directions is bounded between -1 and 1, okay? But quantum mechanics says -3. So clearly, this rules out a local theory for quantum mechanics. Quantum mechanics must be non-local. Okay, now we fast forward 20 years. And then this guy, Nick Herbert, he decided that, oh, this may be useful. Okay, I'm going to use it for something. So he proposed a communication scheme. So he wanted to do faster than light communication. Okay? So he named this proposal FLASH, which is an acronym for First Laser Amplified Superluminum Hookup. Okay? And this is a very early proposal where you actually use entanglement and single particles for technology application. Okay? And he used exactly the same system here. So he used this kind of spin system where you distribute particles, you can store them, and when you want to communicate, you just measure on one side, and then the message should be instantly transferred to the other side. The problem, most people would say then, is that since the measurement outcome on the one side here is totally random, you cannot influence the outcome. Okay? The only thing you can influence is in what direction you measure. But in every direction, the outcome is random. Also on the other side, you will get a random outcome. Okay? So you will get correlations, but you cannot really convey a message from here to here using just this simple measurement technique. But Nick Herbert was a clever man, so he had something up his sleeve. So this is actually what he proposed. So on this slide here, you see this corresponds to a globe in the previous picture. So you have the two particles, a red particle and a blue particle, that go in separate ways. And then you have a removable plate. And this plate, if you put it in, you want to send a 0. And if you do that, this red particle is deflected up here, and you measure the spin in this direction. And then you either get spin up or spin down. You cannot influence it. Okay? So you get either of the outcomes. If you want to send a 1, then you remove the plate, and then the particle is deflected here, and then you measure the spin in this direction instead. Okay? So this is what they can do on one side. You can measure in this direction, you cannot influence the outcome. You can measure in that direction, you cannot influence the outcome. Okay, so what is happening on the other side? So here comes the twin particle, and Nick Herbert then thought, oh, we put an amplifier here. So now at the output, we don't have one particle, we have lots of particles, n particles, where n is a large number. And then we can split these n particles into two beams, and one goes to an analyzer which analyzes in this direction, whether you have spin up or spin down. And in the other arm, you analyze whether in this direction, whether you have spin up and spin down. So if we assume that Alice wants to send a 0, then she inserts the plate, the photon is, or particle is deflected upwards, and then she measures either spin up or spin down, okay? Now she wants to send a 0. Suppose, just for argument's sake, that she gets spin up. She could have got spin down, but she gets spin up, okay? Then we know that the particle here has spin down, right? So now we amplify it. Now we have lots of spin down particles. Half of them go up here, and then they are detected here, and nothing is detected there, because this is the spin down detector, and this is the spin up detector. Half of them go here, But here you measure spin in this direction by a measurement in that direction, and then it becomes totally random, okay? So these two detectors, they will detect a quarter of the particle. Half the particle goes this way, half the particle goes this way, half of them goes here way, so a quarter here and a quarter there. And you get essentially this diagram. So if on one side you measure spin up, then you get n halves here, you get 0 in this detector, you get a quarter here, and you get a quarter here. Should it be spin down, it's these two change places. Here nothing changes. If you change measurement basis here, then you get this, okay? And what you notice is that every row here is different, okay? So you can distinguish the red ones from the blue ones. And that means you can distinguish the zeros from the ones. So actually you send information faster than light, okay? So then, of course, you ask yourself, why didn't someone tell me this? Been around since 1982, and no one told me, okay? Well, the answer is that before you got to read this, Nick Herbert, maybe he wanted to patent it. I don't know if he patented it. He's still alive, so we can ask him. Okay. He sent it to Foundations of Physics for publishing. And Foundations of Physics editor, they sent the paper to this guy, Asher Perez, who incidentally was a student of Nathan Rosen. Okay, so he was well versed in the problem here. Okay, so Asher Perez, he read the paper, and he wrote back to the editor and said, I feel this proposal is totally wrong. Okay? But then he added, but I cannot put my finger on why it's wrong. Okay? But I also feel it's very important we understand why it's wrong, and therefore you should publish it. Okay? So here he gets the paper, he feels it's totally wrong, and then he says, please publish it. And published it was. Here's the result. Okay? And still you can see, so why didn't anyone tell me about this? Okay? And the reason appeared half a year later, because only 6 months later, 2 papers were written almost at the same time. One by Zurek and Wouters, and the other one by Dennis Deeks. And they showed that you cannot perfectly copy or amplify a quantum state. Okay? And the interesting thing is that if there is no separate theorem in quantum mechanics saying you cannot do this, but you can fairly easily, if you follow logic, show that from the foundational theorems of quantum mechanics, this is a result. Quantum mechanics, the postulates of quantum mechanics, which has nothing to do with communication, actually prohibits you to do this amplification. And what is more beautiful, actually, is that if you ask how much noise do you have to add, or is quantum mechanics requiring you to add, the amount is exactly so much that you cannot implement the flash proposal. Okay? In this case, it is a laser amplifier which will add noise, and it will add noise not only in the spin direction that the incoming particle has, it will also add noise in the perpendicular. So it means that this nice division I had in my table is no longer true. All 4 detectors will always fire if you do this, okay? And you will send no information. So Perez's gut feeling was right, okay? Okay, but then some people thought, okay, so you have quantum mechanics prohibits amplification of cloning. What can I use that for? Okay? What can you use it for? Well, one usage is if you want to keep secrets, right? You don't want them to be copied. Okay? So only a few years later, 2 years later, the first proposal for quantum crypto was published. Okay? And this is based on the non-cloning theorem. But I'm not going to talk about this because Professor Zbinden will soon tell you all about this, so I skip. But this really set the ball in motion. So this was, here we start the embryo of the development of the second quantum revolution, where you use actually single quanta and not seldom entanglement. Okay, now we fast forward 10 years. So we had 30 years, 20 years, now it's only 10 years, right? And then I want to speak about the next step that really set off the field of the second quantum revolution, and it was in computing, quantum computing. So the fact is that not all mathematical problems are equally difficult. So I can ask you, for instance, what is the product of 311 and 491? And if I give you this problem, it will take you, if you have a pencil, it will take you probably 5 minutes, and then you can give me the answer. I can also ask you what two numbers gives 152,701 when multiplied. And as you can guess, they are duals, right? So the one is the answer to the other, right? But if I give you a second problem and a paper and a pencil, it will probably take you more than an hour, probably more than that, to figure out the right answer, okay? And so mathematicians, they say that the first problem is polynomially hard. That means that in a polynomial number of steps, you will arrive at the solution. Whereas the second is exponentially hard. And then you say, oh, is there so much difference between a polynomial and an exponential? And the answer is yes. There's lots of difference, okay? And let me give you one example. Okay, so this is a traveling salesman problem. Okay, so we have a number of points that should be interconnected with the shortest path, okay? And the only short algorithm we have for doing this that really gives you the right answer is to compute the length of every path and then compare them. Okay, so if you have 6 paths, then you can start at any of the 6 points, then you can connect it to any of the 5 remaining points, and then you can connect that to the 4 remaining points and so on. So it will take you n factorial, that is, you take the number of points you have, and then you multiply it by the n minus 1, n minus 2, all the way till you get to unity. So many paths is it. And for 6 points, 6 factorial is 720. Actually, you only have to compute half of them, because every path which starts here and ends there, so you will also find if you start there and end there, right? But the factor of 2 now is not important. If I make the problem what appears to be 6 times harder, so say I have 36 points, okay, then you have 10 to the 42 paths. It was 1 with 42 zeros, okay? And you have to compute every one of them and then compare them, okay? So then we can compare that to, for instance, the number of seconds since the Big Bang. It's about 10 to the 18. And then we can think, what is the fastest computer we have today? Well, the fastest computer we have today, they operate in the exaflop range, so about 10 to the 18 operations per second. Okay? So it means that we started the fastest computer at the Big Bang and let it just crunch. We would have computed about 10 to the 38 or 10 to the 40 paths, which is still a little bit shy of this. And if you think that, oh, we could have done it, maybe if I was smart, okay, then I say, well, increase this to 40 points, and then it gets more than 1 billion harder, okay? So you see that there's a hard limit to what, it's the technology. It's not that we're not smart enough. It's just the technology is not there. We don't have the time. So all these kinds of problems are, in essence, unsolvable. Okay, so in 1994, I was working at Stanford University, and one day a postdoc came back from a conference. He was like this, you know, oh, I heard this talk, and this, you know, this is big things. So he heard actually Peter Shor talk about an algorithm, a quantum algorithm. So Peter Shor is a mathematician. He worked at Bell Labs at the time, and he found, so he assumed that, assume I have a quantum computer. They didn't exist then, but he assumed that, suppose I have one. Then he found an algorithm that would actually factor numbers. And not only factor numbers, they did it in polynomial time, not in exponential time. And this was really a breakthrough, okay? Because it gives you the possibility to solve many, many relevant problems in the time we have. We don't have to start at the Big Bang. We don't have to, okay? So Shor's work really opened a completely new field, okay? And it raised many, many fundamental questions. So why are quantum computers faster? Is it really so that they are faster, or is it just that we're not clever enough with classical computers and so on and so forth? Okay? So now we are at the present. So this picture is some of the people, all of them Nobel laureates, who have laid the foundations in one way or another to what we call the second quantum revolution. And what we will get, that are getting out of this, you can see here, there are many, many technology fields that will benefit from this technology. When I made this picture, I made it, and then I said, but this is shocking. This looks exactly like the picture from 2020, no, from 1920, okay? Only men, okay? So I'm very glad that Milena is, you should be happy to have a woman here who is actually doing something about this. And for the females in the audience, I said, men are not smarter than women, right? So please contribute, because if you contribute, you get twice the brain power and everything goes twice as fast. Okay? Promise me that. Okay? So with that, I leave the word to Gerd Leuchs, who will now speak a little bit more about quantum enigmas, I think, and a little bit more about quantum technology, maybe. Thank you.
Buonasera a tutti. Sono felice di essere qui oggi. Thank you for the invitation to come here. Although I have to say Gunnar is a very good friend of mine, but it's hard to speak after him. So, I was told not every one of you is an expert in the quantum era, so I have some elements in my talk which are especially aimed at people who are not specialists in the field. So quantum technology is a hot topic these days. We will see where this goes, and it's fantastic that University of Bari has a special master course. This is very timely, and you set the stage for also others who are following. So the question is that you might ask, what is special about quantum? And Gunnar already hinted at a few, and I will look at it from a slightly different point of view. So in quantum, you have these so-called superposition. So this entanglement is some variation of a complex superposition state. Then you have what people call the observer effect, that observing and how you observe will make a difference. And then, because it's so important, it's mentioned again, entanglement is a superposition, but it's a superposition between composite particles. And you heard already that this is kind of a mind-boggling topic. So a quantum system can be in a superposition of mutually seemingly contradicting states, like Gunnar cannot be here and there at the same time. But there's also something special that happens when you do a measurement. And my plan for today is to have two take-home messages for those of you who have not studied quantum physics yet, and two things that you hopefully also remember still a week or two later. So this is my goal. So one of them is specifically quantum, and the other is not specifically quantum, but very important in quantum. So the one which is very uniquely, specifically quantum, it is what happens when you do a measurement, and strange things do happen. So in general, information is lost. The other one, which is not specific for quantum, but important for quantum, is that calculations become complex, and you're calculating with objects which are not just normal numbers, not even complex numbers, because for these you have a times b is equal to b times a. 3 times 4 is 4 times 3. But there are many objects in the world where this is not true. So this is not uniquely quantum. it happens in many different areas, but it's very important in quantum too. So these two things I hope you will remember after my minutes here. So one, the measurement process. When you observe a water wave, you see the whole wave. In a way, it's a superposition of little waves in different places, so you can see the wave is at several places. But we don't think of much, because when we take a picture with a camera, we see the wave. So it's a one-to-one. It's just an extended object. In quantum physics, we think of the system to also be in quantum physics is a wave theory. So the system is also described by a wave function. Water waves are the only ones we can see. All other waves we cannot see directly. It's not so easy. And in quantum waves, it's the same. We cannot see with our eyes. But we can do some measurements, some detectors. Eventually, we display something on a computer. And then the big difference is when you now do a measurement, and you have, let's see, this is a wave. The coordinate can be position, but it can also be time, some parameter. And you find, you just get one answer. You don't get the whole wave. Then you repeat under identical conditions, and you get another answer, and again, another answer, and another answer. And if you superimpose all these little signals, then eventually you begin to see the wave. And this is the big difference. The wave is there, but you do a measurement, and you don't see the wave, you only see part of it. And the rest is kind of lost in this process. This is what I meant with that quantum measurement is about losing information, getting some information, but also erasing information which was potentially there. So this initially was called the collapse of the wave function, but people think this suggests some dynamics, and to all what we know, it's instantaneous. As fast as your detector, you build a detector faster, this measurement process happens faster. So there doesn't seem to be an internal dynamics. This is not really solved. Nobody can tell you. Maybe at a very fast time, people even speculate that space-time is not continuous. So who knows what the future will bring. So for those of you who have not studied physics, who come from other fields, it's a bit difficult to visualize this, how should I think about it? And of course, this is truly quantum. We don't live in a world which is obviously quantum. Otherwise, we would not have a problem with quantum. If all our world would be quantum, we would be used to this from our young times, from times when we were young. But there's one thing I can offer to you from everyday life, and which is not quantum, but it has some elements of an object which has more information that you can measure, that you can take out by measurement. And these are these pictures you all know, your brain can switch. So this has nothing to do with quantum, but it's the best I can offer to you to tell you a little bit what happens. Actually, this, you know, probably, I'm sure you know this, you can see a younger or older woman. Here you can see a vase, or here you can see a vase or two faces. But I think it's better to use something more abstract. So if you take a cube that you watch from the side and only look at the edges, you can view this cube in two different orientations. So to help you guide your eye, it's either this or this. So in a way, you could say, if you want to have some idea how you should think about the quantum world, this object contains information about this orientation and this orientation. But our brain knows the cube has to be in one direction. So this, I think, is the reason why we cannot see both directions simultaneously. So we can make our brain switch. I think you can all do this when you look at the top picture. But it means when you look at it, you get one of the orientations and then the other is lost. But this is not quantum. We can make our brain switch. In the quantum case, it doesn't work. You do one measurement and you cannot switch back. But at least you can get a little bit of guidance from this. And even you can look at entanglement. And I think if you see these four, basically each of them you can see both ways, but if you see one of them one way, chances are that you see the other ways also the same way. So this is a little bit like this superposition, which was written down by Gunnar with 0 and 1. So here we have, so these special brackets there, these special brackets used in quantum physics to describe states. So it's like a superposition of all four cubes pointing in one direction plus all spheres pointing in the other direction. And now if you do a measurement on the first one, it can be either of the two, depending on how your brain is set up. But when you see the first one in a certain way, then the others, I hope for you, they look the same way. So basically, the projection gives you this. So that means then a second measurement will give you the identical cube. So this shows that you can have very strong correlations. So this is basically very close to what John Bell has been doing and what Gunnar was describing, only with different pictures. So mathematical complexity, superposition states, is something which we find in quantum, but it's not typical quantum. The projection associated with a measurement, this is truly quantum. In many books, I think you learn in school, and I learned in school, this is the wave-particle dualism. I don't really like this so much because I think it suggests something in the wrong direction. With particle, I learned after a while, people refer to what happens in the measurement. I would rather say there is wave, like any other wave, plus this strange projection, what happens with the measurement. So, this is about measurement. So the second point, which is not specifically quantum, which is important, is A times B is not equal B times A. So our normal numbers, the number line is one-dimensional, complex numbers are two-dimensional. There, it's always an equal sign. But as soon as you go to one more dimension, and in mathematics, this happens often, and in quantum physics, even this simplest object, a quantum bit, has basically four parameters. It's a superposition of two states. The coefficients are complex, so you have an amplitude and a phase. The sum of the phase is not so important, so ultimately you have three quantities, two amplitudes and the phase difference. So these are three. So you can, in order to plot this, it's already in 3 dimensions. So it means that in 3 dimensions, multiplications can be rotations. Like, yes, you wanted to pass the ball to me, thank you. And it's not to have it fall on the floor. So now with this ball, I can easily, remember on the very first slide, which was up at 3 o'clock for a long time, a World Day of Quantum had something that looked like a world with longitude and latitude. It was not the world, it was the blogosphere. Very important when you think about quantum. It is very straightforward and has been known by mathematicians for at least maybe 200-300 years that if you have 2 rotations, the effect of doing one rotation after the other, which is like a multiplication of rotation, depends on the sequence. So I will do 2 rotations now, one under the horizontal axis, quarter rotation, and then a quarter rotation around the vertical axis, looking from you to the left. And then I change the sequence. So now the red is up. It's a nice colorful, you can see how the orientation is. So first horizontal axis to you, quarter rotation, then quarter to the left. Remember this? So now I first go to the left and then quarter to you, and it's different. So this is unequal. This is very important in in quantum physics, but not only in quantum physics. So these two are not the same. So that's the other thing to remember, which, and that adds to complexity in calculations. For example, it gives rise to Heisenberg's uncertainty. You could even, I checked because my Mac computer, usually something happens, I quickly look through the slides. So in those of you who studied vector analysis in school, you know there is a cross product. So this is not a group because the unit element is missing. So in mathematics, it's not this high quality of a group, but you can define, so this is a product of two vectors staying in vector space. So the end product is again a vector. And this is not the same. There's a minus sign in front if you exchange them. So this is an example. So this A times B not equal to B times A is very common if you go to higher dimensions. And dimensions for us normal people can be up to 3 to be able to think about it. But in mathematics and in quantum physics, you have many, many higher dimensions, which makes it a bit more mind-boggling. But it's not specifically quantum. Okay, but the same is for waves. You have the fact that it matters which sequence you use in the product is when you talk about conjugate variables like time and frequency, position and momentum, amplitude and phase. You find this all over the place, and for normal waves, not in the quantum domain. If you just do electrical engineering, there's a time bandwidth product. So if eventually you want to make in one parameter you want to make very small, then the conjugate parameter becomes wider. So for example, in optics, if you want to have a small focus, you have to have a wide angular spectrum. So you have to focus very tightly. If you focus only with very small angled beams, then the focus will be much larger. And many examples. And together in combination with the measurement process, this then translates into Heisenberg uncertainty. In the time domain, if you add two different frequencies, then you see that the neighboring peaks, they become a bit smaller. If you add 10 oscillation frequencies, it's more 20. So you can see, in order to have a pulse which is short in time, you need many frequencies. If you want a pulse which is narrow in frequency, you need a wave which is extended over a long, over all of time. So this is true for every wave, but also for quantum waves. So this is this aspect, and this applies to sensing. So, for example, if only one of these parameters is what limits the sensitivity of your sensor, you can make it smaller at the expense of some other quantity getting larger, like time and frequency. But if it's only time you're interested in, that's fine. You can do this. And this works also in the quantum domain. So quantum sensing is about this, for example. If you have like entangled systems, so two variables can all be very noisy, but they can be strongly correlated, and so that gives rise to precise results. And this also is the reason why you can do quantum computing, because when you think about Heisenberg uncertainty, and because of this non-commuting and these uncertainties in the outcome of measurements, you can ask yourself the question, how can it at all be possible to do calculations with a quantum computer if this is governed by uncertainty? I want precise answers. And the answer is, as Gunnar also showed, these two spins, or here these two cubes. You can see, in this case, it's two possibilities. And they are equally probable. So this is the uncertainty. So the uncertainty is like the one or the other possibility of the orientation in case of the cubes. But because of this entanglement, if it's in an entangled state, if you measure the first one, you cannot tell the outcome. But then, you know, the second one, if you measure this, this is very precisely determined. So either the same state or like spin up and spin up, or spin up and spin down, depending on the nature of the entangled state. So you can then have extremely precise correlations, but only when you do this second measurement. So this correlations can be very precise, which is the basis for John Bell's inequalities. So this is, as I said, key to quantum computing. I quickly, so this, the PC messed up my presentation. So this says, this is now an example for intensity correlation, and it says the outcome depends on the measurement. So intensity correlation is like you measure the intensity at different times. It can be the same times or different times, and you multiply them and average. And you can do this by having a single detector, look at the signal, store the time series in a computer, and then calculate the this is called a correlation function, and calculate it in the computer. Or instead of calculating it in a computer, you can split the signal beam in two, have two detectors, have a multiplication here, hardware multiplication in detector box, and then you basically have your correlation already. And the outcome is not the same. And this basically is that the intensity is field operators. There are field operators. They're called A, and A dagger is the kind of the conjugate operator. And these two measurements, two A daggers and A's appear, but in different sequence, and they don't commute. They don't, A dagger is not the same as A dagger A. And as a result, when you do a measurement of intensity correlation, you have to tell how this can be done. Even the second case, when you have two detectors, it can also give you this result if you not use click detectors like here, but if you use other detectors. And there's a very famous experiment which I like a lot, and the hero is Gunnar Björk. This is 2004, 21 years ago. One has to be careful when you describe a measurement. You have to know exactly how the measurement is done and to do the calculation appropriately, because the way you do the measurement influences the outcome, not in a random way. So if you know how to do this, you can go from one result to the other, but it's a bit tricky. Now, in a computer, in a classic computer, you have an input register and an output register. And Saverio was already telling you a little bit about this. So if you have on the input register, one number, you run the processor once and you get the output result. Now, in a quantum calculator, you can put the input register in a superposition of all possible states. So if these are qubits, then there will be 2 to the, if m is the number of slots here, then it would be 2 to the m states, and if these are decimal points, then it would be 10 to the power m. So it's a huge number, even if a moderately sized register. And then in the quantum world, it's fantastic. The quantum processor has to run only once, and it will give you all possible answers. So also the output register is in a superposition of all states. What a big mess. In the input register, we have everything. Output register, we have everything. So what can you make of this? Of course, if you now do a measurement on one side, this is what happens when you do the measurement on a superposition state. Everything collapses to one, and it collapses to the corresponding pair. So when you now do a measurement on the input register, and on the output register, you get the result that corresponds to the input perfectly. But you didn't win anything. So in principle, the quantum computer is massively parallel, but when you do a measurement, you lose it. This is why quantum computers are not superior to classical computers for every given task. It's only special tasks where they can win. And people have discovered some number, but I think many people are working, this is one of the things, people are working on finding problems where this special massive parallelism of quantum computing can make a difference. So in a way, it's a wonderful time because so many things have not been discovered yet. So sometimes I wished, what if I were a bit younger? But then I stopped thinking about this because this is not an option really for me, I think. Or maybe quantum can help. So the problem is the measurement. And in order to give you a little bit of an example, so if you have an input state, and these are qubits, and somehow there is this number n encoded, and you have an ancilla. This is like the output register, and the signal is the input register. So now, in a very, in an extremely simple and trivial example, say the task is calculate the parity of the state. So n could be the number of photons in the state. So n is just a natural number, 1, 2, 3, 4, 5. And if it's 2, it's even, and if it's 3, it's odd. And so sometimes you might also call that the parity of the state. And so if n is even, then we say we want to have the ancilla in, we will put the ancilla into 1. And if n is odd, we put it into 2. So if, for example, if on the input signal is 5, so in binary, 1, 0, 1 is a 5, and the ancilla is in 0, so this is 5, 0, then this processor would say, okay, so 5 is odd, so it will put a 2 in the ancilla state. So the outcome would be 5, 2. But this is still a product state. But if you would put the input in a superposition of many different states, the output would be in an entangled state. So this is a bit trivial because if you look at the number, you know immediately is it even or odd. So, but it's the simplest case where I can show you the essence of it. So you go from a product state to an entangled state, which is not factorizable. So this is basically how quantum computers work. But if you now do a measurement, you project out only one of them. Now you can look at this in this way. So you have in a quantum processor, you can at the same time have many different inputs, and you have many different results, all in parallel. But when you do the measurement, then you lose all the results but one. So there's no advantage. But how about if you don't do a measurement at this point, if you're interested in a quantity, like a global property of the system, where you're only interested in one output, then you can get away with one measurement. So if basically this is like a quantum interference in the quantum domain, so if you go to some quantum interference and look in finally when there is only one output that you need, if you postpone your measurement and do it there, then you will get the answer. And one example is exactly Peter Shor's algorithm. Gunnar was already telling you about it, which is important when you factorize big numbers, which is a difficult task. And there, the difficult, in Shor's algorithm, the difficult, the exponentially hard problem is to determine the period of a function. For this, in a classical computer, you have to calculate each function value. So this takes many steps because this is many different numbers. These can be long periods. But in a quantum computer, you have all this information. If you would do a measurement, you would lose it. But you can do a quantum Fourier transform. Then you go to the spectral domain, and then you, instead of function values that show you the wave, you get in the spectrum, you get for whatever the wavelength is, whatever the frequency is, you get a peak at this particular frequency, and the rest is zero. And then if you do a measurement there, you get the number. And what you're interested in, which number is it? Which is the frequency? Where is it? So this is an example where the massive parallelism of a quantum computer can help. Because in the end, you get away with only one measurement. Then this is important for QKD. But other examples that people talk about, like pharmaceutical companies are interested because if quantum computers, so I think this is why they are about, this is about complex molecules, and there are different configurations, and depending on the configuration, the ground state energy is different. So now you have these hundreds of atoms or thousands of atoms in this complex, and now, but what you're interested in, the configuration of this big molecule is linked to the ground state energy. So the ground state energy is only one number. So by doing the appropriate algorithm, you can use this massive parallelism to get this one ground state energy. So in a nutshell, I think this is why pharmacologists are interested. So there are many applications of quantum science and technology: quantum computers, quantum simulators. This is similar: quantum sensing, quantum communication. Hugo Zbinden will talk about this in a minute. And so this is all what quantum technology promises. There are different systems. When you eventually you have to produce hardware, people working on different systems, superconducting circuits, trapped ions, atoms. Also this, some people try to integrate and miniaturize, which in the end will be important if it's supposed to be of market value. Semiconductor, quantum dots, and even photonics circuits. There are some companies who believe photonics is the way to go. And could be that in the end, as usual, different technologies have different quantum technologies on these different platforms have different benefits, and maybe for one problem, one platform is better, and for the other problem, another platform is better. There are large companies interested. There are young startups who were founded especially to do quantum science and technology. There are many national projects, a European project like the European flagship was my first slide. And in Germany we had a big program, but I think here in Italy, in France, so in many different countries, there's a big program. So my take-home message is, and this is another thing that was gobbled up, but I think you can guess. So these are the two things. So for those of you who are not from physics, remember A times B is not necessarily B times A. And the measurement process, think of the cube. What happens when the measurement process, how you lose information. The cube, before you look at it, has information about both these cubes, and when you look, you see only one cube, right? So that's, I think I'm a bit over time. Sorry for that. And then I hand over to Hugo. Thank you.
Okay. Well, thank you very much for the invitation. I'm pleased to be here. Are you still awake? Are you still have some energy? Excellent. So I try to be a bit shorter. And I will try to answer this question. Now, you have learned a lot about these very strange things, no superposition, entanglement, and so on. Now, it will be much more down to earth, and we ask ourselves, are these strange phenomena can be used for something practical? So, well, before I talk about quantum cryptography, I will talk about classical cryptography. And you may know, nowadays, if you encrypt data, we have two kind of schemes. One is this DS and ES. This means that you use a random key, rather short key, to encrypt some data, and then also the same key to decrypt some data. Of course, this key must be random and must be secret. And then we have this RSA scheme, which is called public key system, because it consists of a public key and a private key. So you can use a public key in order to encrypt a message, but only the owner of a private key can decrypt the message. And now if you go on the internet and want to make some shopping on Amazon or something, you should not do that, no, because it's an American company, we should buy local stuff. But suppose you do this, then what do? You want to, of course, exchange some information, your credit card number or something like this. So you go actually on the internet, your browser will get the public key of Amazon, and then on your computer, you generate a short key, type DS or AS, and then you encrypt this short key with a public key of Amazon. You send it to Amazon, and Amazon will decrypt it because Amazon is the owner of a private key, of a public key system, and then you share both symmetric key, and then you can start communicating. It's a bit complicated. Why do we go first for a public key and then to this short secret key? Well, the reason is that, of course, I have never met Mr. Amazon, so we cannot exchange directly the secret key. And also because if we are able to do everything with this RSA, it will consume much too much resources. That's why I use this RSA only to exchange a private key, and then I work with a private key, not with a short key. Okay, now, as you heard before, we have this RSA is based on the idea that there's something like a one-way function, like this factorization of big integers. You have seen that before. It's very complicated to factorize, but it's easy to calculate the product. So that's a one-way function. But now, Mr. Shor actually found out that the quantum computer is no longer a one-way function. It goes very well in both directions. So this means that this way to do cryptography is actually not secure. Okay. So we would like to do something else. And there is another protocol which is very easy and is perfectly secure. It's called the one-time pad. In this case, you have your message you want to encrypt, the plain text. And you need a random key, which is as long as this text, and you use it only once. That's why one-time pad. And if you do this, you can easily figure out, that if this key is completely random, then this cipher text will also be completely random. Something which is completely random, by definition, doesn't contain any information. In this case, of course, you have a problem that you need to distribute these very long keys. Okay, so we have two things. We have this classical cryptography and the quantum key distribution. And for both, what we need to begin with is actually random numbers. You need random numbers to generate random keys, independent if it's a quantum or classical. So I will talk first about random numbers, because also here, it's actually quantum physics can present the solution. No? And here, for instance, what you could try, you could have a source of single photons and send it on a beam splitter, and you say, okay, if a photon is reflected, it's a 0. If it goes straight through, it's a 1. And this is a nice feature of quantum physics. We have this inherent randomness. So if you have a photon like this, there's no way to predict if it will be reflected or transmitted. And in a particular, if this photon here, let's say, is reflected, you have no idea what the next photon will do. No? Okay, so by doing like this, indeed, you can generate random numbers. Of course, there are some technical issues, like always. But as you can see here, it was this kind of random number generator based on this exists, and actually it was commercialized by a startup company of University. Well, you see, it's still pretty big and clumsy and a bit complicated. No? So maybe there's another way to generate random numbers based on quantum randomness. And, well, you can consider the case where you have a camera, like on your mobile phone. And if you have a constant flow of photons, or pulses of photons, whatever, or constant flow of light, I should say, since the fact that it's composed by photons means that actually, if you have even if you have a constant intensity, actually per time interval, the number of photons will fluctuate. It's a statistical effect, no? And actually, you know that this number of photons have a Poisson distribution. It looks like this, no? So even if the average number of photons is constant, sometimes you will have a bit more photons, sometimes a bit less. And also, this is a completely random phenomenon based on quantum mechanics. So if you have a good camera, nowadays the cameras have very, very little noise, very intrinsic noise, electronic noise. You see this here, in this distribution here, if I send it the photons, 410 photons, I get this green curve here. It's a very nice Gaussian distribution. If I do nothing, I have only very little contribution here, this electronic noise. So as soon as this quantum noise is bigger than the electronic noise, you can extract through quantum. You can see that if you want, you can see that here in more formulas. Now this variation, this sigma of this number of photons you detect is given by the number of photons sent in and this probability to detect photons plus this noise. Okay, so with this very simple detector, you can generate quantum randomness. So if you now, for instance, at the output of your camera, you have an ADC, and you, let's say in this case, if you take a 10-bit ADC per pixel, you know that at the very end, the least significant bit, this will not be random, or it will be dominated by a classical noise. We don't want to do that, And these bits here are not random neither, because it's kind of like 400, But in between, we have a lot of random bits. We can extract them. So this has the advantage that this is very small, and it's very cheap to produce. And here you have an example, this phone. Actually, I have one here. So in this phone, you have a little chip which generates random numbers. So whenever you make a transaction or something, you send some money to somebody, you need these random numbers, and it can be generated by a chip. So this is probably the quantum device which has been sold most of times, because it, unfortunately, in Europe is not yet available. But it has been sold maybe 1 million times in Korea. It's some really practical quantum technology. Okay, so that's for random number generator. Now let's go for a quantum key distribution, and I will try to be quite simple. So what do we need? What is the resources to make quantum key distributions? And, well, first, what we need is, we need some random numbers on both sides for Alice and Bob. Then we have a quantum channel, an optical fiber. We can send photons through this channel. And then we need also actually an authenticated classical channel. This means that at some point Alice and Bob need to communicate in an authenticated way. It's kind of obvious now, if you want to exchange information, secret information with somebody, you must have met this person at some point beforehand and exchange some authentication. Then once you have this, you can continue to generate keys and communicate in a secret way. So how does it work? So Alice sends photons to Bob, and now we use this fact that what actually Gerd mentioned before, if you have a quantum state and the eavesdropper tries to make some measurement, he will perturb the measurement and we detect this. That's the idea. So before Alice and Bob eventually use the key, they will compare parts of the key, check if there are errors, or too much errors, there are always a bit errors. And if they are not too much errors, they know the key is good enough, and then we have some procedure, they make error correction and privacy amplification. This means that the remaining little bit of information Eve could have can be reduced to 0. And then they obtain a secret key. That is a principle. Another thing which is very important also, of course, which I didn't know, Alice and Bob need to be in a secure office. No? It's not very useful to have a secret way to communicate, and the eavesdropper sits behind you and looks at your screen. No? And that's something we should not forget. No? In practice, for us, no, maybe the communication is not the most weak element. No? So it's much safer to communicate with these algorithms and so on, but probably your apartment is not that safe. No? So in my case, for instance, in Geneva, twice somebody broke into my apartment, but never happened to me that somebody got my credit card number. Anyway, so now, well, that's a first picture of one of the first experiments which was done 30 years ago. And this is an example of an experiment we made in my group a bit more recently, 7 years ago. And it's actually just to highlight that even if it's, we're talking about quantum physics, quantum key distribution, whatever, it's actually a lot about technology. So in order to make a very nice experiment, you need a lot of electronics, you need good optical fibers. The detectors are very, very important. So we develop ourselves low noise superconducting detectors and so on. So it's a multidisciplinary thing. No? You need also, of course, mathematicians. You make all these algorithms. You need this privacy application, error correction, all these things. It's a very complex thing. Now, I don't want to go too much detail, but to give you an idea how we do that. No? What is our protocol? Our protocol is actually very simple. We just we send bits, no 0 and 1s, and we say, okay, the 0 is a pulse at a certain time, and the 1 is a pulse a bit later. We have this what we call a time bin qubit. The light can be sent at time 1 or at time 2. So we can encrypt data. Bob, on the other side, just measures the arrival time of the photons and knows if it's of 0. So now, by doing this, of course, it's not secure at all. Eve can do the same and resend the pulse. So we need to add some features, no? And a feature we add this superposition state here now, which is now here the photon is a superposition of being in the early or in the late. And now we also had on the receiver side, we had this interferometer. So whenever the photon takes this path here, the early part can go here and the later part, and we can have interference here. And this allows us to see if this kind of states went through without being perturbed. Now, if an eavesdropper, she wants to find out if we have sent this state here or this state here. She makes a measurement to see, is there a photon here? Then she will destroy this superposition between this, in this X state, no? So this, if she will provoke a collapse, or Gerd said we will lose some information. After a measurement, we don't have any more information of the coherence if you do this thing. And so if Eve now tries to find out which state is sent here, and of course she does not know that from time to time we send this X state, she will generate errors. This means that at some point these detectors will click where normally they shouldn't click. Because we are just actually interferometer in a way that normally all photons go out here. If something is perturbed here, we get a click here. Well, that's a detail. I think I can skip that now. Thing is, or I will make it very short, we don't use single photons, we use weak coherent pulse. And that's a bit the problem, because as I told you before with a random number generator, if we have weak light, we have a distribution of number of photons, and sometimes we have two photons, not only one. And if you have two photons, of course, the eavesdropper can exploit that. In order to prevent that, we vary the intensity, and we can trick the eavesdropper, and so we can still distill secret keys. And now, well, that's how it looks like a bit more in practice. Now we have a laser, we generate laser pulses, then we send them in an interferometer, we have this train of pulses here now, and then if it's an intensity modulator, we can carve out these patterns and generate this state, or this state. Send it to Bob, and Bob, as before, detects the arrival times here or checks for the coherence with this interferometer. Well, in a lab, it looks a bit messier, no? This is kind of all the setup of Alice. It's not even Bob here. And then, as I said, you need a lot of additional features. You need a lot of electronic synchronization, and then all this procedure shifting, error correction, privacy amplification, and so on and so on. And so that's the way it looked in the lab in the first generation. Now it looks like this. So we can integrate everything on a single chip. So it becomes potentially very compact and easier to industrialize. Maybe a last word, and I will stop, about performance of these systems. No? We have a limit in distance, no? Because we send very weak signals, and of course we have attenuation, and at some point, very rarely photons arrive at the very end, and we also have some detector noise, and eventually the noise will, or the signal will be hidden in the noise. So if we don't have noise at all, this would be a decay of our rate as a function of distance, just due to the absorption of the optical fiber, which is very low, but still, no? So you see, it's a logarithmic scale, no? It's an exponential decay. Now, since we have this, we have two effects. Now, at some point, it will break down. And the reason is because we have this noise, and also because we need time to make the distillation. We have to accumulate a lot of data in order to make this privacy application and so on. So this gives us, for kind of an ideal system, a limit of 600 kilometers, with very low rate then. No? And there is another way now to do that, which came up, where you can go further than that. And this way, I will not go into detail, I will stop here, but just to give you the idea, in this scheme, what you actually do, you have a very, very big interferometer, you send some strong pulse here to Alice and to Bob. And then from here, you send weak pulses to the center and make a measurement here. And by doing this, you essentially can double the distance. Because in some way, a photon only has to travel from Bob to the center, or from Alice to the center, but it's only half of the distance. So that brings up to this kind of. And then, if you want to go further like this, you can go to satellites. There is some schemes of quantum repeaters involving quantum memories, where you use entanglement and so on and so forth. But I think it's already late, so I stop here. Thank you very much for your attention.
Proseguiamo l'applauso per i tre professori Gunnar Björk, Gerd Leuchs e Hugo Zbinden. Allora, se abbiamo ancora qualche minuto, io passerei a questo punto anche a qualche domanda che immagino naturalmente voi abbiate per i professori. Sentitevi liberi naturalmente di alzare la mano eventualmente e abbiamo sicuramente i microfoni che possono passare per i ragazzi. Some question for you, ok? Naturalmente se l'avete per qualche professore in particolare indicatelo, altrimenti risponderanno loro.
Hi, I'm a bachelor student in this department. I wanted to ask to whoever professor wants to answer, essentially, but it is specifically aimed to Professor Leuchs. If right now we talked about the problem of the collapse of the wave function, this still is in debate. And I wanted to, I don't know if there are any experiments or any ideas in this moment in physics that actually try to investigate what happens when it comes to dynamics to the collapse of the wave function. Because in the bachelor course, teachers, we have, basic courses have to tell us that there is a problem. There's kind of, there is no explanation in this moment. But I wanted to understand if there are any ways, any experiments that investigate the dynamics of the collapse of the wave function in today's physics. Thank you.
Yeah, so maybe I can start since you asked me directly. I can start with an anecdote and then answer your question. The anecdote is when I was about your age, plus minus, I started to work in a laser lab. And people told me, when you put your CW laser on a photodiode and take the signal to an oscilloscope, you see a noisy trace. And if you do spectral analysis of the noise frequencies, you see at low frequencies, you see big noise. And when you go to somewhat higher frequencies, eventually the noise rolls off, but it doesn't go to zero, it levels out. There's white noise. So this low part, this additional noise is technical noise because the laser, something is oscillating, maybe there's some thermal noise. But this plateau, this is quantum noise, and it goes to infinity. And I remember at that time, I was thinking, how can something fluctuate, because this is about quantum fluctuation, right? How can something fluctuate infinitely fast? After all, this is intensity. This means electric field fluctuates infinitely fast. So in Maxwell's equation, you have dE dt. This creates curl of magnetic field. There should be huge magnetic fields. This is really strange. But then it was kind of down in my guts, so it subconsciously bothered me for many, many years, until much later, when I started to give lectures myself, suddenly it occurred to me, there's nothing that fluctuates before I do a measurement. So the fluctuation is basically a result of the measurement. Before, there is this wave function which has some extension, some variance, but nothing fluctuates. It's like an extended wave. And when you do a measurement, you project to one. And the thing people told me, this goes to infinity, was not exactly true because nobody checked. Nobody can measure infinitely fast. But what it means is no matter how much you try to build a faster detector, if you have a faster detector, that's the speed at which it happens. So this is the end of the anecdote, and I already got into the answer. There are experiments, but at the moment, all experiments indicate that the measurement happens essentially instantly. So I think there's no one who can tell you why this is. I think it's at the level of a law of nature. Nobody can tell you why gravitational, what is the gravitational force. We can describe it, we can do 1 over r squared, but we cannot say what is it, why is there attraction. So in physics there are limits to where we can answer questions. So basically we go to something which we then call natural law of nature, and then there's no further explanation. But in physics, you always question this. Is it really the last step? And it could be that sometimes later one finds, oh, you can go one step more. This was not the limiting law of nature. Maybe there's something more. I know of very few people who were thinking about this, that maybe one should try, and what does it mean that the answer comes seemingly infinitely fast? Can one check this more? So it could be that although measurement process can be faster and faster because technology developed, we can now do measurements in optics at the attosecond level. But even at that level, it seems that the projection is instantaneous. But it doesn't mean that it will be instantaneous if you look even much faster. Only now there is no hint. And very few people are thinking about this, but not many.
Hello, here, just curious person actually. Congratulations, very nice presentation first of all. And I'm just curious from the hardware side, technological point of view. As some of you showed, actually there are several different ideas how to realize a quantum computer. Might be quantum dots, might be trapped ions, or might be optical tweezer, and so on. What do you think from your personal perspective, if there is one technological solution which is like in front, like a most probable, or closer to actually production, a true production recipe implementation, sorry. And what is the role of Europe in the hardware development in comparison to USA and China? That's it.
Okay, maybe I will make you disappointed, but first of all, a quantum computer is not a universal computer, okay? Every quantum computer has its limitations, what you can do and what you cannot do. On your own PC, you can implement whatever algorithm you want, and it will do it. But this is not the case for quantum computers, because at least any existing quantum computer today doesn't have full connectivity. Every qubit does not speak to every other qubit. So my personal answer to your question is that different quantum computer platforms are going to be used for different things. Okay? There's not going to be one solution, there are going to be several solutions. Some solutions maybe will turn out to be impractical or too expensive or whatever. Okay? But this is too early to say which one is which, right? Okay? Then your second sort of, where is Europe posed as compared to the US? If you take the largest quantum computers that exist, I think the largest I know of is IBM's latest version. It has a little bit over 1,000 qubits, as I recall it, and it's also modular, okay? So actually, the current 1,000 qubit computer consists of 2 computers interconnected with optical fiber, okay? And then you can connect more of them, so they are going to increase this. But already there you see that, oh, it's not going to be fully interconnected, right? So there are problems you cannot solve on that computer. So again, I see that everyone works on his or her solution, and many of the solutions will find its application, okay? And maybe some of them are more important than others. This, I think, again, is too early to judge.
Yeah, maybe I can add that all these, so there's no quantum computer in the version that we would dream of, where you could do the calculations that computer scientists would like to do. We are far away from this. And the different platforms, they all have their own challenges. They're not the same. In some platform, the coherence is less of an issue, but then like in a photonic quantum computer, the decoherence is less of an issue, but the coupling between photons is much more difficult. Whereas in other platforms, the challenges are different. And one thing that is being developed in sync is quantum error correction, because when they don't work perfectly, you need to do quantum error correction to come closer to this. So I think at the moment the decoherence and the deficiencies of the quantum bits is such that you need about 20 real quantum bits to have one pure logical quantum bit. And these 19 others, you need to do quantum error correction. So there's limits. So if you have 400 qubits, effectively you have only 20. And 20 qubits, anything that you can do with 20 qubits is you can easily do on a big classical computer also. So this, we are in basically quantum computing. The concept is more or less clear. There are different architectures that they are clear, and one architecture is more better fits better to one platform than to the other. But there are technical problems, partly fundamental, partly technical, partly engineering has to be done in all these platforms. So it's at this point, I think nobody can tell you, which is why people invest on all these platforms. If it would be clear which platform would win, you would not find people to invest their money in other platforms, I think. So I think it's too early to say.
Altre domande? Ce l'abbiamo lì.
Good evening. I'm still at my first year of university here in Uniba, and I'm curious to ask if being optimistic, is it possible for artificial intelligence to measure a quantum?
I think we didn't understand. Can you repeat?
Is it to be optimistic? Is it possible to measure a quantum through artificial intelligence?
Well, artificial intelligence is not a cure to everything. You have to. This is a very general question. I think to actually measure a quantum bit is a hardware object, and you need some hardware for this at first. I think artificial intelligence is once you have many qubits and you have this information, what you do with this big data, there artificial intelligence can help. Well, actually no, in my institute there is one guy, I forgot his name. He was with Zalinger, Mario. Mario is the first name. It will come back to me. And he uses kind of like machine learning, kind of artificial intelligence, machine learning to optimize measurement procedures? What would be the best way to kind of extract the information out of your quantum bit or whatever you have? So I think, because when you build the experiment, you have different elements that you put together, and if the number of them is big enough, you have different choices, and so there I think somewhere between machine learning and artificial intelligence, this may help to find the optimum solution. So yeah, I think this is where it might help.
Other questions?
The name is Mario Kren. He's working on this.
Professor David.
K-R-E-N-N. Mario Kren. He's working on this.
Yes, thank you. Thank you. Very good presentation and very interesting presentation. I have a question for Professor Zbinden. Is that I mean the idea that I have is like making examinations in the universities that the more you try to avoid students to copy, the more they get smarter and find a way to copy, in a way. So that it is not that we will eventually to sort out to some kind of quantum non-demolition measurements that can allow us to make a reasonably good copy without that actually we destroy the entanglements and this information, or this is completely, let's say, impossible by the fundamental limits?
Well, of course, the security proofs, they don't put any limit to the eavesdropper. No? Eavesdropper can do whatever he wants, so he can make the best quantum measurement. Well, actually, it's Gunnar, you mentioned this cloning, no? And it's quite interesting. Of course, if you could clone, then you could hack a QKD system, no? And you can try to clone, but only up to a certain fidelity. And you can show that with this kind of fidelity, you cannot win more information. But actually, something which came into my mind when you mentioned that is it's quite funny. So the fidelity of the cloning depends on the intensity of your light pulse, no? Or a single photon or a weak coherent pulse. If the intensity is very big, you can make a perfect clone. No? If the intensity is small, you get a fidelity which is smaller, and for a single photon, the fidelity is 2/3, if I'm not mistaken. So now, the fact that there is a relationship between the incoming intensity and the fidelity, you can actually use that to make a power meter which is calibrated. Because you just send in, let's say, a certain polarization state, you amplify it, you measure the polarization at the output, you can estimate the fidelity, and knowing the fidelity, you know how much light you sent in. And you don't need another reference, and it's a tool for metrology. And we made the experiment that it works perfectly fine. So it's not the answer to the question, but the answer is, well, somehow it's an answer. No, you can do the best you can do, but the proofs, of course, include all these kind of things you could think about. So it's
okay. I think we can.
Can I
sorry.
add something? So I think this concept of quantum non-demolition or back-action evading measurement, it's a little bit misleading because it sounds like you can bypass the no-cloning theorem. This is not true. So whatever you do, this is a very basic, this was proven by very basic considerations. It's basically the least perturbation, or maybe some aspect of the quantum system you don't affect, but you hide the result, the back action of the measurement in some other Hilbert subspace, but you don't get around the no cloning theorem. Actually, this reminds me when Gunnar he was very kind when he gave his talk and mentioned Nick Herbert, and that the editor of was it Foundation of Physics? Yeah, sent it to Asher Paris. He also sent it to a second referee. Was it not Girardi? I think, yeah. So I think in Asher Paris, in the book, he is writing about this. And this is a lesson you can learn. So Girardi knew why it was wrong. He wrote the 4 lines down in his referee report, which later Zurek and Wouters published in Nature, in the famous no-cloning theorem, and told the editor, look, it's wrong. This is the proof. Kind of reject the paper. But he followed Asher Paris, and then Wouters and Zurek read it, and they basically put down the same lines that Girardi was putting in his review, and they became famous with this. And this poor Girardi, I feel so sorry. So he could have been famous had he been quiet and said, this is wrong, don't reject, but not telling why, and instead publishing immediately his own take on this, or prepare and wait on the day after the paper or he didn't. Now, I think probably, he was probably thinking it will not be published because he rejected. And so he was not even thinking it would be published. So he was probably not thinking it's worse to talk about it because it's so much nonsense. But it really tells you how things can go and how you become more or less famous. And so it's an interesting part of the story. Yes, yeah.
Ok, penso abbiamo terminato. Facciamo un applauso ai nostri ospiti, Professor Zbinden, Leuchs e Björk.